So let's say someone said we wanted to write down what the class was. Co-16B, today is the 13th of February. So consider we want to find the average value of f of x equal to 3x squared plus 2x plus 1 on the interval from 1 to 3. Basically, the idea is that you're trying to level out this function, for lack of a better word. So if we picture this as kind of, and again, this isn't going to be a perfect drawing, but here's the idea. Imagine you've got like a glass of water and someone has kind of bumped it so that the water is no longer level. And that's your function. Well, when the water settles back to its equilibrium, that level is the average value of the function, where essentially the area under the function hasn't changed, but now we're talking about one singular height as opposed to many different heights. So when this levels out, whatever that level value is, this is the average height or the average value. And the thing to kind of remember here is that this area, I want a different color. This area here under f of x, and this area here under the average value of f of x are the same areas. Do we need to know any of this to be able to actually calculate average value? No. Calculating average value is super duper straightforward. You take the normal area integral that you would usually calculate and divide by the length of the interval. So here, to calculate the average value, it's going to equal 1 over the length of the interval. So 1 over 3 minus 1. Or, well, yeah, times the integral from 1 to 3 of your function. 3x squared plus 2x plus 1. You might write it as 1 over 3 minus 1 times integral. You might write it as the integral divided by 3 minus 1. Either way, you're just taking the area and dividing by the length. Oh, and length times height equals area. So area divided by length should give you height, or the average height, the average value. So if someone says find average value, all you have to do is take the integral and then divide by however long your interval is. So here, it's going to be 1/2 times, we're going to integrate this thing, it's going to be, let's see, 3x cubed over 3 plus 2x squared over 2. Someone pick some nice numbers here, plus 1x from 1 to 3. So it's going to be 1/2 times 3 cubed plus 3 squared plus 3 minus 1 cubed plus 1 squared plus 1. Let's see, 27 plus 9 is 36, plus 3 is 39, minus 3 is 36. So 1/2 times 36 is 18. Just to be super clear here, the area under the curve is 36, and then the average value over the interval is going to be 36 divided by 2, which is 18. And in my opinion, there's not a lot else to say about average value. Like really kind of nothing else to say. So I won't say anything else, unless there's any questions about average value. We really like, and then I saw there was and I also point out, like, so on his practice test, on my practice test, he gave you an integral question, and then the next question about average value you shouldn't repeat the work you've done, right? Like if you look at his practice midterm here. Let's see here. There's problem like 4 or 5. Yeah. The problem 4, you're doing the integral from 1 to 3 of 1 plus x squared, and then problem 4a, and then problem 4b, find the average value of, I don't know why you would write it backwards, maybe just to be slightly confusing, right? But it's the same function over the same interval. So you're just going to take whatever this answer is here. Let's pretend this answer was 42. And then your answer here would be 42 divided by 3 minus 1, which is 21. But you don't need to show any of the work of doing the integral here because you've already done it here. So don't do more work than you have to. Yeah. Right. So like here, I mean, maybe I like, so you could say that the average value here would be equal to 1 over 3 minus 1 integral from 1 to 3 of x squared plus 1 dx. But then since we already did that integral up here, and I'm pretending like it's equal to 42, I don't actually think it's equal to 42. But whatever it's equal to up here, that number, that gets to go right there. And so you just get 1/2 times whatever that value was.
So all you need to show is 42.
Exactly. Yep. Right. I imagine, I mean, right, his tests are usually pretty similar to his practice test. So I imagine he will do something similar to this, where he will ask you an integral and then ask you to find the average value of the function that you just integrated. So take the integral you found, divide by the length of your interval. Let's see what's in the chat here. Well, they asked, I don't know. I'm not the one writing the test. It's possible you could be asked to graph. They certainly did on this practice test, right? There was one, I think it was problem 5, where they asked you to sketch the region defined by this integral. So probably. So he's going to post things that we should memorize. Do you know? I do not know where you can find that. I'm sure it's somewhere on Canvas, but I don't know. As far as what to memorize, again, that depends on what's on the things that you're going to be given. So that's really a question that's better for him, not for me. We can talk about that a little bit more after we get through the other things we should get through. All right, so average value, you probably are expected to know how to find the average value, but again, it's just the integral divided by whatever the length of the interval is. Well, so let's look at midpoint rule. Again, I imagine there'll probably be like one question about the midpoint rule. There was one question about the midpoint rule in the practice test. Midpoint rule is really just kind of, I don't know. I don't see a lot of value in it, but it is something we do sometimes because some functions cannot be anti-differentiated. And when you can't use the fundamental theorem of calculus to find the area under a curve, sometimes we use the midpoint rule to approximate the area under the curve. This example we're going to do is not an example where you would have to use the midpoint rule, where you could just anti-differentiate it, but we're going to use the midpoint rule anyway. So let's say we're going to use the midpoint rule. I guess I didn't say what it was yet, but fine. Rule with n equal to 4 subintervals to approximate or estimate the integral from 1 to 5 of 1 over x dx. And we'll do the actual answer as well. So here's the idea. You're taking your function, which is 1 over x, and which will draw it kind of exaggerated here. Over the interval from 1 to 5. 1, 5. And hopefully the problem they've given you, the length of your interval divides nicely by the number of subintervals. And here that's the case, right? The length of our interval is 4. The number of subintervals is also 4, and 4 divided by 4 is 1. So our delta x here, which is the width of each subinterval, is equal to b minus a over n, which in this particular case is 5 minus 1 divided by 4. Right, whenever someone says b and a, we know they're talking about the top limit of integration and the bottom limit of integration. But that's always what b and a are, or a and b, bottom and top. That's going to be 4 over 4, which is 1. So we're going to break this interval from 1 to 5 up into 4 equal subintervals. So we're just gonna say 1, and then 1 plus 1 is 2, and then 2 plus 1 is 3, and then 3 plus 1 is 4, 4 plus 1 is 5. Those are our subintervals. Each subinterval has a width of delta x. So right, so that's delta x. Same deal here. All of these subintervals have the same width. Now what we're going to do is we're going to try to approximate the area of each subinterval with a rectangle. And there's lots of different ways of doing this. You can either use the left endpoint to give you the height and use a rectangle that was too big, or the right endpoint to draw the rectangle and do a rectangle that's too small. But we're going to use the midpoint to try to get a better approximation. So right here, there's our first midpoint. And at that midpoint, we're going to use that midpoint to find the height of the function there. So watch for a second. This rectangle with a base of 1 and a height of whatever the function is equal to at that midpoint, that's going to be how we find the area of that first rectangle. So easiest way to find the midpoint, I think, is to think of it as an average. Right, the middle of two things is just the average of those two things, and the average of 1 and 2 is 1 plus 2 divided by 2. So the midpoint here is 1 plus 2 over 2, which is 3/2. And then the height of the function is f of 3/2. We have to plug in our midpoint to our function to get the height. So the height here, that height is f of 3/2. And if f of x is 1 over x, then f of 3/2 is 1 over 3/2, which is 2/3. And then we're gonna do the same thing for each subinterval. So here, now there's a couple different ways you can find the rest of the midpoints. You can keep averaging. The average of 2 and 3 is 2 plus 3 over 2, 5/2. The average of 3 and 4 is 7/2. The average of 4 and 5 is 9/2. Or if you think it's easier, you can take your first midpoint and then add your delta x to that midpoint to get the next one. So 3/2 plus 1 is 5/2. 5/2 plus 1 is 7/2. 7/2 plus 1 is 9/2. Either way you want to do it. I imagine he won't give you terrible numbers on the test, but I don't know if he could. I really don't think he would. So then we're going to find the rest of the heights. So what we're going to do here is we're going to say that the area is approximately equal to the width delta x, the base of my rectangle, times the height of my first rectangle. And then the base times the height of the second rectangle. And then the base times the height of the third rectangle. And then the base times the height of the fourth rectangle. Notably, the base factors out, right? That delta x I can factor out from each of these and say I've just got delta x times f of m1 plus f of m2 plus f of however many midpoints I'm using. Sorry, there's 2 plus signs there, there should not be. So in this particular example, my delta x is 1. My midpoints are 3/2, 5/2, 7/2, 9/2. And then we actually plug them into the function. Now the reciprocal function is just going to take each fraction and give me the reciprocal. So that should give me f of 3/2, which is 2/3, f of 5/2, which is 2/5, f of 7/2, which is 2/7, and f of 9/2, which is 2/9. If you add all this together, you get approximately 1.58. Which again, if it were an exam situation, you wouldn't have a calculator. I wouldn't recommend trying to get a common denominator here. I would leave my answer as this. This is my approximation using 4 subintervals with the midpoint rule of the area under this curve. Yeah. Correct. Yeah, delta x is literally the width of each subinterval, which you're going to get from however long your total interval is divided by the number of subintervals. In this case, it happens to be 4 divided by 4. But we could have a different example where each subinterval had a different width, which we'll do in a second. N is the number of subintervals, and it's going to be prescribed to you. They're going to tell you, you do the approximation with n equal to 2 subintervals, or n equal to 4, or n equal to 6. Probably 2 or 4, somewhere not too big. 4 is a pretty typical choice. And then just so you know, although this is certainly not a required part of this, I actually wanted to find the area under this curve. The actual area, since we can actually find it. If we do the integral here, the integral from 1 to 5 of 1 over x is going to be, well, the antiderivative of 1 over x is the natural log of the absolute value of x from 1 to 5. Plug in 5, natural log of 5, minus plug in 1, natural log of 1. Natural log of 1 is 0. So this is equal to the natural log of 5. And if you use a calculator, that's approximately 1.61. So our answer here, our estimate, 1.58, is a pretty good estimate of the actual value, which is close to 1.61. Again, we're not going to be asked to show that, but that's kind of the idea here. Is that, oh yeah, this approximation, and if we'd used more subintervals, we would have gotten a better approximation. So why would you do this? Because there are some functions that we can't antidifferentiate. The most common examples being something like e to the x squared, e to the negative x squared, sine of x squared. All those functions are functions that do not have an antiderivative. And so instead of trying to find the area under them, you could do something like this where we approximate it. Let's see here. Yeah, let's do one more example. We don't want to do that. Sure. All right, I'll throw one more example at you and then we will move on. Let's keep track of where your papers are going, James. Okay, let's say we want to approximate. So one more midpoint rule. We'll make this one slightly more challenging to find the midpoints. So we're going to approximate the integral from not 1 to 3 again, James. It's so boring. Let's say 2 to 4 of e to the x squared using still n equal to 4 subintervals. And honestly, I think the easiest way to find the midpoints is to draw the x-axis. I don't worry about the y-axis of the function, but draw the x-axis. So we're going to go from 2 to 4 and give yourself plenty of space. There we have 2 to 4. All right, I want all of you very quickly to find what delta x is supposed to be for this problem. Give you 20 seconds. Right, delta x is going to be 4 minus 2 divided by 4, which is 2/4, which is 1/2. So then we're going to find all of our endpoints. So we're breaking this up into 4 equal subintervals. It's going to look like this. Right, I broke that up into 4 equal sections. If it's 4 sections or a multiple of 2, I usually cut it in half first. And then if it's 4, I just cut those in half again. And then to get each of these endpoints, which are not my midpoints, I'm just going to add delta x. So this is going to be 2 plus 1/2. And you can use decimals or fractions. I prefer fractions, but I'll write both. This is 2.5. This is 3. This is 3.5. This is 4. Or if you prefer, this is 5/2 and 7/2. If you like. Either way. And then to find the midpoints, we're doing some averages. Again, you might prefer decimals, you might prefer fractions. I think it's easier to see with decimals here personally. The midpoint here, the midpoint of 2 and 2.5 is 2 1/4, 2.25. Do not write 2 1/4. No mixed fractions, not allowed. It's probably fine allowed, but like you should either write 2 1/4 or you should write 9/4. You really should not, I know I said 2 1/4, I wrote 2.25 because I just can't, but 0.25 is a quarter, but don't write 2 1/4. Someone's gonna be giving me multiplication. You don't. Okay, so first midpoint's 2 1/4, 2.25 or 9/4. If you were trying to do this in more of a fractiony way, you might consider that as 4/2, that's 6/2, that's 7/2, that's 8/2. And so then if you want to find the midpoint or the average of these two numbers, 4/2 plus 5/2 is 9/2, divided by 2 gives you, 9/4. 5/2 plus 6/2 is 11/2, divided by 2 is going to give you 11/4. And then 13/4. I'm just adding 1/2. 11/4 plus 2/4 is 13/4. 13/4 plus 2/2 plus 2/4 is 15/4. Those are my midpoints. And then we're going to toss the formula at it. So again, here's our formula for the area using midpoints. So I don't really have a good notation for this. I guess, no, I do. The notation is M4. It's the midpoint rule approximation using 4 subintervals. That's pretty standard notation. And it's going to be equal to my delta x times f of my first midpoint plus f of my second midpoint all the way to f of my fourth midpoint. In this particular example, that's going to be delta x, which we found to be 1/2 times f of 9/4 plus f of 11/4 plus f of 13/4 plus f of 15/4. What's my function? Right, I can't leave it like this. I can't just write f of whatever. I actually use the function. What is my function? Right, it's the function that we're supposed to be trying to integrate, that we can't integrate typically. So then, and again, if this is a test situation, here's where I'm going to stop. I'm going to write this as 1/2 times, it'd be kind of gross, e to the 9/4 squared plus e to the 11/4 squared plus e to the 13/4 squared plus e to the 15/4 squared. The only thing you could reasonably do more than this is actually square those. So you could, I guess, write this as e to the 81/16 plus e to the 121/16 plus e to the 169/16 plus e to the 225/16. But I don't think you should. Even if you can, even if you're good at that, don't waste your time. I don't really think that's worth anything, actually. Really, like, I don't think going from here to the next step is worth any credit at all. Unless he specifically says, simplify as much as you possibly can, which I don't think is his vibe at all. So leave it like that. And that's kind of it when it comes to the midpoint rule. You find your subinterval length. You find your endpoints first in blue. And then you find the midpoints of each subinterval. I think using averages is the easiest way for me to conceptualize it. I imagine his numbers are probably going to be easier than this. Typically they are. And then you do your width times all of your function values added together. The function gets evaluated at each midpoint. We add all those heights together, then multiply all those heights added together by the singular base to get our approximation of the area under the curve. Cool. All right. Any questions about the midpoint rule before we move on to talking about volume? Okay, let's talk about volume. I should say volumes of revolution. Section 5.7. Volume. All right, and we'll just use some examples because examples are the easiest way to see this. So let's say we want to find the volume of the solid formed when the region in quadrant 1 bounded by y equals x cubed, y equals 0, and x equals 2 is revolved around the x-axis. And let me actually ask you all a question for either class. Have you done any revolving around the y-axis? Okay, that's kind of what I thought. So then we won't talk about that. It's really, I mean, the process is the same. You're just using different variables, but we'll just stick to the x-axis for now. So I think for problems where you're revolving around the axis, you really kind of need to draw the region. We did a little in Lee's yesterday. Okay. Well, I think maybe we'll do examples like that on Thursday. I don't want to confuse the people that have a test on this tomorrow by talking about by doing it that way. Yeah, cool. It's really not much harder to do it the other way. Oh, that's not what I want to do. Okay, great. So I do think though it's really, really important to draw the picture if you can. It's not absolutely necessary, but I find it hard to do without. Unfortunately, the pictures are usually not too hard to draw. So I'm going to draw the function y equals x cubed. I'm only focusing on what's happening in quadrant 1. So I'm not going to draw the part down here in quadrant 3. I mean, I might draw a little bit of it, to be honest. But then here's my function looking something like this. And it can be super exaggerated. It doesn't have to be like a perfect depiction of the function, as long as it's got the general right kind of gist. So there's y equals x cubed. And then I have y equals 0, which is the x-axis. Don't get that confused, right? Y equals 0 is the x-axis, x equals 0 is the y-axis. And then x equals 2 is some vertical line over here. So this region that has all 3 of those curves as boundaries is the region that we're trying to revolve around the x-axis. Okay. I would always recommend the following. You're going to draw a strip, a very narrow rectangle in your region that is perpendicular to the axis of rotation. Always. That's always true in the 16 series because we only do the disk/washer method. If you're taking the 21 series, we can talk about the shell method, then sometimes parallel is fine. But for us, we have no choices. We are automatically having to draw a vertical strip, which is perpendicular to our horizontal axis of rotation. And here's what's going to happen. We're going to imagine that this vertical strip, this rectangle, is getting revolved around the axis and is sweeping out the shape of a disk. So when we revolve this, and this is where hopefully my drawing skills hold up here. When we revolve this thing here, what happens is, let me just do this part first. This little strip revolves around and makes a disk. And the volume, there we go. And the volume of this disk, well, it's a circle with some thickness. So the area of the circle is pi r squared. And the thickness, the width of this disk is a small change in x, which I'm going to write as dx. Some people use delta x. I use dx because I know we're going to integrate this thing. Doesn't really matter which way you write it. So this small change here is dx. What's the radius of my disk? Well, it depends on what point I have picked in my region here, right? If I go a distance of x from the origin, then the height here depends on how far I am, right? The further right I go, the larger my radius actually is. It's just the function. So the radius here is going to be x cubed, right? If x is 1, my radius is 1. If x is 1/2, my radius is 1/8. If x is 3/2, my radius is whatever 3/2 cubed is. But in general, this radius here is just x cubed. So here, the volume of my disk is really pi times x cubed squared dx. Okay. But that's the area of one disk. Oh, sorry, that's the volume of one disk. I want the volume of all the disks. And this is where my drawing skills are not going to hold up. I should have brought the book with me. The book has some really nice pictures of like all these discs kind of stacked on top of each other. Like there's like this, there's like one of the first examples is like a cone, and then they have like all these little like slices of the cone stacked up. So like the idea here is, right, we're doing all of these little rectangles, and then we're revolving them all around to get more and more disks. So that we are estimating, right, the area under this shape that is getting revolved around the y-axis. So that's the idea. We're trying to find the volume of this kind of cone-ish looking thing. And the way we're finding it is by adding up, in quotes, all of these volumes of disks, but really when we add them up, we let the widths get smaller and smaller and smaller, and we take the limit and we end up using an integral. So the way we're going to find the total volume is we're going to quote unquote add up all of the volumes from as far left as x equals 0, because that's as far left as this shape goes, to as far right as x equals 2. The setup is usually the hard part here. The solving here is not terrible at all. We're going to do the integral from 0 to 2. It's almost always the case that we like to pull this pi out in front, although it's by no means necessary. X cubed squared is x to the 6th. Then we antidifferentiate. The antiderivative of x to the 6th is x to the 7th over 7 from 0 to 2. We plug in 2 and we get pi times 2 to the 7th over 7. Minus we plug in 0 and we get pi times 0 to the 7th over 7. That's just you should not write that. I mean, you can write it right now, but like on your test, if you can see that plugging in 0 is going to give you 0, you can probably get it without writing it. I will say, make sure that plugging in 0 actually gets you 0. Two notable exceptions: cosine of 0 is equal to 1. E to the 0 is equal to 1. So if you have those kinds of functions showing up when you're plugging in 0 for a definite integral, make sure you're actually thinking about plugging in 0 and that not everything's going to be 0. So here you would just get pi times 2 to the 7th over 7. And 2 to the 7th is what? 128? Sure. 128 pi over 7. Or just leave it as 2 to the 7th pi over 7. So that's the very general idea about how to find the volume of revolution. You do pi times your function squared dx, and then you integrate from as far left to as far right. Now, sometimes things are not quite so easy. Let me get my frame. Yeah. Sorry, I ruined it. Ruined everything. I have ruined everything. Okay, well, let me just move this picture here instead. That's the easier way to fix this. Great, cool. Okay, so let's do some more examples here. What time is it? Oh yeah, we have loads of time. Loads of time. So you should definitely, we won't do too much volume here, because again, at least for those of you in Kubernetes class, there's probably only going to be one volume question. Right? Like, I guess you could put 2 on there, but I wouldn't bet on it. None of these examples are what I really want, so I'll just make something up. Yeah, okay. So I assume, although I don't know, he's talked about the disk and the washer method. They're the same, by the way. The disk is just kind of the easier version of the washer method. So how do we know when to use which? Well, again, drawing the region is really how I know. I knew I was going to use the disk method here because the region I drew was flush with the axis of rotation. Right? The whole way, this region is touching the thing it's being revolved around. Another way to think about this is your axis of rotation, y equals 0, which is the x-axis, is one of the boundaries of your region. Let's do a different problem. Let's say now, again, writing these problems out is half the battle here. We want to find the volume of the solid obtained by revolving the region bounded by, what do I like here? Sure. Y equal to the square root of x and y equal to, sure, 1/3 x. Is that going to work for me? Yeah, that's fine. Again, around the x-axis. And I'm going to draw these regions here. Now, you might want to take a moment to find where they intersect each other. But I'm actually going to say that's not generally true. At least you don't want to waste your time doing the algebra because usually the points are going to be nice. Here's what I mean. Let's just graph these. Y equals square root of x is a very kind of general graph. We should know how to graph it. It's going to look something like this. And y equal to 1/3 x is a straight line. It's not steeper than this at the origin. We do know that they touch at the origin, right? For sure. If you plug in 0 for x, both of these things equal 0. I know it's going to be underneath this other function. And now I really would like to know the point where they intersect because it's going to be the limit of integration for my integral. I know that my integral is going to start at x equals 0 and it's going to end at whatever this point of intersection is here. And instead of, setting these equal to each other and solving is not that much work usually, but sometimes it is. You could also just guess. And I might not guess 7 because the square root of 7 is trash. Right? I'm going to guess numbers that are easy to evaluate, like 4. What's the square root of 4? What's 1/3 times 4? Not 2. Or I might guess 1, but that's not going to work either. Or I might guess 9. The square root of 9 is 3. 1/3 times 9 is 3. So make smart guesses when you're trying to find points of intersection. If you don't want to, right? You could also say square root of x equals 1/3 x, and then you could square both sides. X equals 1/9 times x squared, and then you could do whatever magic you need to do. But this feels like way more work than I want to do. Yeah, it is 9x equals x squared. X squared minus 9. I'm writing too much. I could have already guessed it by now. There's all the work you could do. But again, I think you can get away without doing all that work personally. Either way you slice it, you're going to have the point 9,3 and the point 0,0. And then just like last time, for our region here, and here's our region that we're trying to revolve, we're going to draw a strip in the region perpendicular to the axis of rotation. And at this juncture, since our axis is always going to be the horizontal x-axis, our strip is always going to be a vertical strip. Notice that this vertical strip, this region here, is not flush with the x-axis. And when you revolve this around, you're going to be missing some middle part. In fact, just do it over here. If I take this strip and revolve it around, I'm going to be missing the entire middle here. Get something that looks like that. Oh yeah, that's a washer. That's why we call it the washer method. And the volume of my washer is going to equal, well, it's the area of the larger circle. I'm going to say the larger circle has a radius of capital R. So it's going to be pi times big R squared minus the area of the smaller circle. So I'm going to say it has an area of pi times little r squared. All times the thickness or the width, which is still a small change in x. Here, my larger radius is the function that's further away from the axis of rotation. Now, I will point out y equals the square root of x is not always further away, right? Namely, way over here, y equals the square root of x is actually the closer function. But in the region that matters, y equal to the square root of x is further away from the axis of rotation than y equal to 1/3 x. So this volume of my washer is going to be pi times the larger function squared, square root of x. I should be more specific with my word choice there. My function that is further from the axis of rotation squared. Minus pi times my function that's closer to the axis of rotation, which is 1/3 x squared. All that times dx. And if I'd been a little bit smarter there, I would have factored out the pi. So that's the volume of one washer. And now we're going to quote unquote add up all the washers by integrating. So our total volume is going to be, and let's just pull that pi out in front. Be pi times the integral of the large radius squared minus the smaller radius squared. From as far left as the left boundary of the region, x equals 0, to as far right as the right boundary of the region, which is x equal to 9. So just as a recap before we finish this problem off, if your region is flush with the axis of rotation, it's just the integral of pi times your function squared dx. If your region is not flush, then it's pi times the further away function squared minus pi times the closer function squared. Let me factor out the pi. So big radius, little radius versus just one radius. Also, I'll point out, you also going to see we were going to need to use the washer method here because my axis of rotation was the x-axis, which is the line y equals 0, and that wasn't one of my boundaries. My boundaries were y equal root x and y equals 1/3 x. Cool. Or the picture really though, right? You can see that there's all this space. And then finally here, well, not finally, doing the work, square root of x squared is x, 1/3 x squared is 1/9 x squared. We integrate, we get x squared over 2 minus 1/9 times x cubed over 3 from 0 to 9. Now here's a great place to make some smart moves. So I plug in 9, let's see what happens. I get pi times 9 squared over 9. I don't care what 9 squared is because I'm just going to cancel one of the 9's. 9 squared over 9 is just 9. Minus 1/9 times 9 cubed over 3. And let's make the same smart choice here. 9 cubed divided by 9 is going to be a 9 squared. And then 9 squared divided by 3. I really don't want to think about 81 divided by 3. I want to think about 9 times 9 divided by 3. Or 9 times 3, which is 27. So doing, and then minus 0, minus 0. I don't want minus 0. But I guess I will because I like you guys. And then that's going to equal pi times 9 minus, we said this was going to be, I'm feeling worried here. Feeling real worried here. Yeah, we're gonna have to, so sometimes you make mistakes. We're gonna figure out what went wrong here. Yeah, did I make a mistake? I must have, yeah. Right, because I said this was 9 cubed over 9. Yeah, 27. Does anyone see the problem here? What's 9 minus 27? Negative 18. Our volume shouldn't have been negative. So I've clearly made an error somewhere. Let's see if we can figure out where it is. Do these really intersect at 9? Yep, square root of 9 is 3. 9 times 1/3 is 3. This is certainly the larger function. Also, if you're not sure which one's the larger function, like the graph should make it clear, but you can also pick a point between 0 and 9 and test it to see which one's bigger. So like if I pick the point 4, square root of 4 is 2. 1/3 times 4 is 4/3, which is smaller than 2. So the square root function is the larger function. Squaring them both, I get x. Oh, I'm dumb. No, I'm not dumb. No. I feel like I'm dumb because I'm not figuring out what's going on here. Square root of x squared is x. 1/3 x squared is 1/9 x squared. We anti-differentiate. Oh, that's okay. I see where I made a mistake. I anti-differentiated x, and what did I get? What should I have gotten? What's the antiderivative of x to the first power? X squared over 2. I don't know where that 9 came from. Sometimes you just see all these 9s, you get carried away. Sorry about that. So this should have been x squared over 2, not x squared over 9. And then this should have been not 9 squared over 9, but 9 squared over 2. Nothing cancels there. So that really should have been 81 over 2. Woof. So then you have not 9, but 81 over 2 minus 27. And that's going to be pi times 81 minus 54 all over 2. And 81 minus 54, I think, is 27. So you end up with 27 pi over 2. If that answer, right, if we hadn't looked at that, we wouldn't have seen that we made a mistake, but seeing that we were getting a negative answer and knowing that that shouldn't happen when you have a volume, definitely made us have to look back and be like, oh, there's definitely an error somewhere. Let's go find it. Sometimes you just make stupid mistakes because I don't know, you see all these 9s, you're like, there should be a 9. I have no idea why I wrote the 9 there. It's very curious to me. Questions about this? Okay. So drawing the region, I think, is kind of vital. Yeah. Should we do another example? Should we not? All right, let's pause for a second. Are there any questions from Tavernet's practice exam that you would like me to visit? I see that there's quite a few U substitution problems on there. I'll point that out. Sure. Let's see. No, I should have it somewhere up here. I guess you could also, but also you could just read it to me.
Okay, so it's fine, but in the column of when you can x times LMX, then the LMX is squared.
Yeah. So the integral of 1 over x times natural log of x squared. Right? Cool. Yeah, it's a good problem. 2c. Is it 2c? Yeah, okay. So how to best think about this? So typically, if I would say generally, if there are natural logs in your integral, it almost always means we're going to have to do a u sub or later on integration by parts. So, because there isn't really a way of integrating natural log of x without one of those two methods. Since we don't have integration by parts as a tool yet, u sub is really the only thing we could think about using here. So what's a good potential choice for you? Right. So here's what I would say generally. I would always start with a simpler choice for you versus a more complicated choice for you. So if I had to choose between letting u equal the natural log of x or letting u equal the natural log of x quantity squared, I would make this choice here because it's the simpler of the two. And then if that doesn't work out, then go on to the more complicated thing. There are two good reasons why this is maybe the better choice. The first reason is it's stuck. And you can make that argument for both choices here. But the natural log of x is stuck inside of being squared. Also in the denominator. But yes, I feel like one could convincingly argue that the natural log of x squared is also stuck inside the denominator. So, okay, that argument doesn't hold a lot of water. But the second more compelling argument, and definitely the du dx part is the more compelling piece of evidence, always, is that the derivative here, what's the derivative of the natural log of x? Right. So du is 1 over x times dx versus over here, just if we were to look at it, the derivative of the natural log of x squared would be 2 times your stuff to the first power times the derivative of your stuff. And the problem with this choice would be that I don't have a natural log of x times a 1 over x times dx. Whereas here, I definitely do have a 1 over x times dx. So I would probably make the choice to slightly rewrite this just to make it super duper obvious. I would write this as 1 over the natural log of x squared times 1 over x times dx. And then I would be like, oh yeah, this 1 over x dx, that is my du. literally, right? du is equal to 1 over x times dx. You can do this differently if you like, but this is the way I think it works the nicest. And then this here, that's going to be my 1 over u squared. So I'm going to rewrite this integral just using the variable u and no x's. 1 over u squared du. But after you've made that change, then you still have to integrate. So doing the u substitution is only half the battle. Then you still have to actually find the antiderivative. To do this here, I would definitely rewrite this as the integral of u to the negative second. So it's not a log, it's a power rule. Integral of u to the negative second is u to the negative second plus 1 divided by negative 2 plus 1. In fact, it's almost always a power rule, unless it's 1 over u to the first, or u to the negative first. Plus c. Make sure you remember those plus c's. For every indefinite integral, which most of the integrals on this exam are going to be indefinite, as soon as you stopped writing this integral symbol and started writing what the integral actually is equal to, you have to write the plus c. And then here, I need to switch back. I wouldn't leave it like this. I would write this as either u to the negative 1 over negative 1 plus c, or honestly, negative u to the negative 1 plus c, or really negative 1 over u plus c. That's more of a personal preference, to be honest. You'd probably be perfect. I can't leave it like this. You'd be perfectly fine with this choice or this choice, but then we plug back in what u is equal to, because if it's indefinite, you have to end with the same variable you started with. I started with x's, I got to end with x's. It's going to be negative 1 over the natural log of x plus c. Here's an interesting question that I imagine someone might be asking themselves in their head. Why isn't it the natural log of the absolute value of x? Or maybe not. Maybe no one's asking that question. But if you are asking that question, the reason why is because we didn't actually ever integrate 1 over x. The integral of 1 over x is the natural log of the absolute value of x. But this natural log of x is just showing up organically as a choice for you. There's no need to add in an extra absolute value. In fact, it would be wrong to add an extra absolute value unless you're actually doing the integral of 1 over x or 1 over u. Yeah. The reason I mentioned this is because sorry. Oh, you see something? Sorry. Yeah. There's like a piece of almond in my mouth. Gross. I was eating almonds earlier, but still like, okay. Anyway, oftentimes people say like, oh, natural log, we're used to seeing the natural log of the absolute value of x, but that's only true when we actually do the integral of the function that gets us there. All right. Other things. I can also just go through problems in the test, but like, if you have specific questions, I'm happy to address them. Let's see, what do I think looks worthwhile here? Ooh, yeah, we should do that one. Let's look at 2B. I'll give you a different slice. I'll give you 2 different versions of this problem. Let's look at something like this. The integral of, sure, 4 over 3 plus e to the negative 2x. I feel like I'm very not straight. Okay. So this kind of problem, I feel like has kind of 2 different ways you can get there. The easier way to deal with a problem like this, and really you don't have to do this problem until you've seen it once. Like it's a problem that just requires experience. The thing you want to do here is multiply the top and bottom by e to the opposite signed power. So I want to rewrite this as the integral of 4 over 3 plus e to the negative 2x times e to the 2x over e to the 2x. It's not the only way to get there, but it is the easiest way to get there. I'll show you the other way if you all want to see it. So then on top, we have 4e to the 2x. And the denominator, 3 times e to the 2x is 3e to the 2x. And e to the negative 2x times e to the 2x, we add those powers. And those powers add to what? And e to the 0 is 1. And then after you've done this trickery, you then make a u substitution, letting u equal the denominator. So we're going to let u equal 3e to the 2x plus 1. And our derivative, our du, is going to equal the derivative of 3e to the 2x plus 1, which is 3e to the 2x times 2, because of the chain rule. And then we slap on the dx there. And then I see an e to the 2x times dx. So I'm going to rewrite this as, I'd probably pull the 4 out in front. That seems natural to me. 4 integral of 1 over 3e to the 2x plus 1 times e to the 2x dx. And then I would take this du over here and isolate the things on the right-hand side that I want. So I would choose to write this as 1/6 du equal to e to the 2x dx. You can do this differently if you prefer. You could isolate dx and then say dx is du over 6e to the 2x and do it that way if you like. I don't like it that way, but fine. So then this e to the 2x dx is going to equal 1/6 times du. And this whole part here is going to equal 1 over u. So then we rewrite it. We rewrite it as 4 times the integral of 1 over u times 1/6 du. I would pull the 1/6 out in front and write it as 4/6 times the integral of 1 over u du. Reduce the 4/6 to 2/3. The integral of 1 over u is the natural log of the absolute value of u. And since I've integrated, what do I need to write now? Plus c. And then finally, we have to go back to the variable we started with. So we're going to rewrite this as 2/3 natural log of the absolute value of our choice for u, which was 3e to the 2x plus 1 plus c. And it's kind of a funky problem. The other way of getting there, if you don't like doing it this way, is it's fine, but it just feels cumbersome. But the other way of getting there would be to take your original expression here and rewrite this for the integral of 4 over 3 plus e to the negative 2x dx as 4 over 3 plus 1 over e to the positive 2x. And then get the common denominator in the bottom. So it's going to be the integral of 4 over 3e to the 2x over e to the 2x plus 1 over e to the 2x. But it feels like a lot of writing. Then it's 4 over 3e to the 2x plus 1 over e to the 2x. And then finally, you flip and multiply, and you get the integral of 4 times the reciprocal e to the 2x over 3e to the 2x plus 1, which then you could write as 4e to the 2x over 3e to the 2x plus 1. Seems like a lot of steps to get to the same place we got to up here, which is just through one step. Also, another reason why I don't like doing it this way is it's not, I think, a huge leap to change e to the negative 2x to 1 over e to the 2x. It seems like maybe a semi-obvious choice. Obviously, probably not right, but like it's not like, okay, I understand why you would do that. On the other hand, if the initial integral you were given was, say, the integral of 1 over, I don't know, 2 plus e to the positive 3x, then it really feels unnatural to me to rewrite this in the same sort of way. To write this as 1 over 2 plus 1 over e to the negative 3x just seems like a strange choice. Like a choice you would only make because you know what's supposed to happen anyway. So here I would definitely say the choice you would make here would be to write this as 1 over 2 plus e to the 3x. And then we're multiplying the top and bottom by what? Exactly. And then you would end up getting the integral of e to the negative 3x over 2e to the negative 3x plus 1. And then you would do this the same sort of way we just did the previous one. You would let u equal the denominator. The derivative would be essentially the numerator off by a constant multiple of some sort. And then we would do the same process. I imagine there'll be a question like that. I mean, I imagine the actual test is going to look very similar in content to this actual practice test, so. So I would definitely encourage you all to do the practice test, the iris, because pretty similar, but not too similar. What time is it? Okay, let's see. I think there was something else I observed that looked like it was interesting to look at. Again, if anyone else has requests, I'm happy to take them. I'm just kind of looking through here. Yeah. Maybe. If you tell me what it is, sure. Okay, yeah. Please, they tell you that was f prime of x is equal to what? And then they also tell us the f of 1 is equal to. Cool. And that x greater than 0 part is not really important. Like I'm sure it felt like it was important to mention, but as far as solving this situation, it's probably not going to be useful at all. So we're trying to find our job when you're trying to solve the initial value problem is essentially means find f of x. That's what we're trying to do. We're trying to find the function f of x. So if I know the derivative of f of x, how do I find f of x? What do I do to the derivative to get back to the original function? Right, we integrate. So we're going to do we're going to say that f of x is going to equal the integral of x squared minus 5 divided by x squared. I suppose if you really wanted to make things harder on yourselves, you could do this with long division, but that's not necessary here. If you have a rational expression, a fractional thing, and your denominator has one single term, we can just divide each thing in the numerator by that single term. So we can totally rewrite this as the integral of x squared divided by x squared minus 5 divided by x squared, which we should then rewrite again. Like you all should rewrite this. Simplify that. Rewrite it in a way that makes it easy as possible to integrate. So hopefully that is what you're coming up with. 1 minus 5x to the negative 2. We're going to integrate. For some reason, the integral of 1 always throws people off. The antiderivative of 1 is just x, because the derivative of x is just 1. Just like the antiderivative of 6 would be 6x, or the antiderivative of negative 7 would be negative 7x. And the antiderivative of a constant is just that constant multiplied by x. And then when we integrate this, we get negative 5x to the negative 1 divided by negative 1. Plus c. And the plus c part here is extra important because part of solving the initial value problem is figuring out the actual value for the constant c. So I would simplify this. I would say that f of x is equal to x. Negative 5 divided by negative 1 is positive 5. And I would write this as, instead of plus 5x to the negative first, I would probably prefer to write it as x plus 5 over x plus c. Although either way is probably fine. Now we're going to use our initial condition, which is f of 1 equal to 2, to solve for c. So we're going to plug in x equal to 1. So f of 1 is equal to 1 plus 5 divided by 1 plus c. And that should equal how much? 2. So then we can solve for c. 1 plus 5 plus c equals 2. So 6 plus c equals 2. So c equals 2 minus 6, which is negative 4. And if you stopped here, it probably wouldn't hurt you, maybe, but I wouldn't. To actually solve the initial value problem, you should be writing the function with the value of c plugged in for the constant there. So our actual answer should be that f of x is equal to x plus 5 over x plus -4 or just -4. That's the actual way we should finish this question. Yeah, let's see. I'm gonna look at one of these other ones here real quick. So I will point out there are a couple questions on this practice test to ask you to sketch some things. And I kind of really want to look at 5B for a second. The 5B says to sketch the region defined by the integral, sorry, -1 to 1 of 1 minus x squared minus x squared minus 1. And technically, there's more than one right answer to this question. But I can tell you by the way it's written what he wants you to do. What he wants you to do here is he wants you to think of this first function here in parentheses as the top function, and the second function here being subtracted as the bottom function. And we can certainly graph those. We know that y equal to x squared minus 1, which is my bottom function. I'm going to draw that one first because it's easier for me to draw. The bottom function is just your normal parabola shifted 1 down. So it's something like this. Notably with intercepts of 1 and -1. The other function is actually the reflection of that, right? 1 minus x squared is your downward opening parabola shifted 1 up. So the top is really y equal to 1 minus x squared, which looks like that with the same intercepts of -1 and 1. So what he's hoping you will graph here now, again, don't graph this like a circle because parabolas do not have circular shapes. They're a little more pointy. Is your parabola like that? Oh gosh, he says it doesn't really draw very well. And then the bottom part, I would, if you had a different color on you, I might use a different color. Like that. That's what he wants you to draw. There's the region. Now, technically, if you did something else that I think would be kind of crazy, you could still be right. Here's what I mean. You could simplify the inside of this integral. 1 minus x squared minus 1. That would simplify as, well, let's see. 1 minus 1 is 2. And minus x squared is minus 2x squared. You could totally graph the parabola 2 minus 2x squared if you really wanted. If you really wanted to take a risk and try to maybe get it right while still making someone think about your question, I wouldn't recommend doing this. This is not what they want you to do. Someone's gonna look at this and be like, what are they doing? Oh, I guess technically they're right. I have to give them credit for this, but don't make your graders work harder than they need to. But if you wanted to graph this, right? If you plug in 1, 2 minus 2 is 0. You plug in -1, 2 minus 2 is 0. If you plug in 0, 2 minus 0 is 2. So it looks like this parabola. And technically, that region would also be correct. But don't do that. I feel bad even showing it to you, to be honest. Like I should pretend that's not even there. Do it the right way. Do it the way that you're expected to do it. Because that's what they want you to see. They want you to see that the area between these two functions is the top function minus the bottom function, and vice versa. That the integral of the top function minus the bottom function is the area between those two functions. Okay. That said, if for some reason graphing these two functions seemed really hard, and somehow it was easier to graph the difference of them simplified, then you could get away with doing something like this and at least hope for some partial credit. Maybe all credit, I don't know. But I can't imagine that's going to be the case where doing this is going to be easier than doing that. I will point out something to observe here, and this is true of the problem that I wrote on the practice exam as well, is that at the limits of integration, both functions do have the same value. Right? If you plug in 1 here and 1 here, you get 0 and 0. If you plug in -1 here and -1 here, you get 0 and 0. So they are intersecting, and they're also both hitting the x-axis, which is extra nice. So it's meant to be a nice closed region that doesn't have weird like openness to it. Okay.